So you should be able to see my presentation here, Modal Analysis with Head Acoustics. Okay, so the agenda we'll start with today is an introduction. Basically, how did we get here? Recording modal analysis data will be the second item we go to. Analyze investigating modes, and then finally comparing mode results. Finishing with a summary. So, Head Acoustics, known for acoustics. After all, acoustics is in our name. Sound quality expertise, binaural recording and playback, innovative sound quality analysis, and to mimic human hearing, sensitivity since the 1980s. Definitely what we've been known for. We did add multi-channel data acquisition available in the 90s to acquire vibration side of the traditional NVH engineer's role. NVH is noise and vibration. We know that noise is caused by vibration, and some type of investigation is naturally of interest to NVH engineers. So modal analysis was possible, but the data acquisition part was understood, basically in situ, maybe also with some hammer impacts, but definitely the analysis, the mode shape investigation was done with Vibrant ME Scope. So much of the ME Scope role now has been brought into the suite tools within ArtemiS SUITE, and this really started with version 11.5. 12.5 added modal analysis, and then 13.0 moved our impact measurement to the family of structural modules. So no shaker control is not available at this time, but we are taking major steps. There we go, advancing this. We are taking major steps in modal analysis capabilities with hopes for even more progress in the near future. So now moving on to recording modal analysis. How do we do it? So one of the most important steps is, rather than just random vibrations, which you keep track of where the points are, that you're taking that vibration, all shape investigations require a structure. So where does that come from? There's options for you can do an internet search for compatible file types, as shown here. There is also a way where you could provide input, say via an Excel template import, where you could have a spreadsheet of points, lines, and surfaces. And there is a tutorial in ArtemiS SUITE version 13.1, I believe, showing a template on that. Contact us if you have more questions on that. So, or you can make the point line by line, or point by point and line by line in a measurement point library. So you can add points, and then you can position the points globally via the properties page. And then you can link the points as well as group points. For instance, here I have a simulated seat back, where the green is the seat back and the yellow is the seat bottom. So there's our ways to make those points manually to come up with a quick and dirty structure of your own. So investigating how a structure or component vibrates in situ, you can use recorder and ODS or time domain analysis or recording on this. So you can use SUITE Recorder to record all the time data. You can place sensors based on the structure. And then you can use ArtemiS SUITE to calculate transfer functions coherence for use with the model connections. So the video here showing on the screen, hopefully, is an example from our YouTube International page on operating deflection shapes. So feel free to review that for a quick tutorial on how easy it is to set up an ODS with ArtemiS SUITE. So points being created and lines connected, and also points being created added to a downloaded structure. Tails continue to check his sensors and orientation, connected to HeadLab, and easily connect sensors within ArtemiS SUITE Recorder, and then also orientating the sensors as well. So how is modal analysis data recorded? So you impact a structure to understand the mode, shapes, or nodes, and impact measurement or modal analysis. And modal analysis, that's how you get the two together. You can use impact measurement workflow, which will be shown here shortly, where you can set up your measurement type. Is it a roving hammer or roving accelerometer? You can set up your accels on your structure, and then where you can tie it to a measurement point library. And you can automatically set common recording needs. Again, I'll show that here in the video. Impact measurement workflow really makes things easy on you to automatically set up, automatically take, automatically advance the points that you're making measurements at. And then finally, it allows you to save transfer functions as well as some commonly used file types. Time data might be of interest. Coherence also might be of interest. So I will go now to the sharing of the video that I took for this example. Okay, we're going to show an impact measurement here with a roving hammer. For simplicity's sake, I have completed the first portions of this project, this workflow, where I've entered in a folder, and I'm continuing a project here, brake rotor 1. Moving on, I can enter in some documentation to describe what type of test I'm taking or what modifications have been made to the structure, test date, any comments. We can also create a template or edit a template, have more information here if we want to. Moving on, we go into our point and labeling setup. So I have imported a brake rotor measurement point library where I have 20 points on the main rotor and 5 points on the hub, all with exciting in the Z direction. And then I have added a fixed data point for the response, and that's going to be at 0.4, and that's right there. Moving on. Okay, here's where we select the sensors to be used with the channels. I've added a hammer and a triaxial accelerometer to channels 3 through 6. And I'm okay with the orientation that we currently have for the accelerometer, measuring in the Z direction. Moving on. So here's where we set up our parameters for the impact. This can be done automatically or manually. With the automatic option, it will choose the sampling rate, the block size, the delta F associated, any type of excitation or response windowing that's needed, from a trigger threshold to a pre-trigger. That all can be automatically set. So we can start that process automatically here. It's waiting for a trigger. So I'll tap the rotor and work our way around the rotor to make sure we get some good impacts. All right, after a sufficient number of impacts and looking at the data, it's able to determine that the configuration can be completed now. All our parameters have been automatically adjusted. If we did want to make those changes right now, we could as well, and say that we wanted to change our sampling rate by clicking that manual configuration. Okay, continuing on, we'll start the actual test. Here it's confirming that we want to start tapping at 0.1 and measuring at 0.4, and I will continue with that. And also we have the option here to set up the number of strikes, so I'll set up 3 here, and we can auto reject on a bounce, an overload, an underload, or a bad coherence. A coherence limit I can change here if I would like to, and I would like to go to 500 to 5,000. You can choose your transfer function type. Many options here to choose from. Right now we'll do accelerants or just typical FRF. you do have the option to save not only the time data coherences in the autospectra for each point, for the excitation, excuse me, but also those other different transfer function type measurements. You can here as well change the excitation and response window if you want to. All right, with that, we will get started with point 1. So it was good impact, good when it comes to ranges, no underload, and coherence will be measured on the second hit. But if I were to have a double hit, a bounce, that would automatically be rejected. If I were to have a overload, that would be rejected. If I would have a bad coherence, say tapping off of the structure, that would be rejected as well. So we'll go back to point 1 and make a good impact and continue on. That was accepted. So after the third proper strike, we're able to complete our recording for that point and moving on to point 2 and still keeping our accelerometer in a fixed reference point. We'll continue on and we'll go through the rest of the recording, rest of the data acquisition. Okay, the outer ring is complete. Now I'll start the inner ring. Okay, the inner ring is complete. Now I'll start on the hub, 5 measurements on the top where the hub is. Okay, after all points are measured, we're given that indication, and all points have been measured. All FRFs that we've asked to save, as well as the time data, have also been saved, and we can continue on. All right, so this is what else we can do with the data. If we did have more data to transfer, we could look at that in a data viewer right now. We could save that to a report or create a report from it, whether it be creating it new or using an existing report. We could also export all of this data to these selected file formats. And that's it for the data acquisition. All right, so continuing on, so that was an idea on what our impact measurement workflow can do. You can also do measurements standalone with the SQuadriga 3. So with the appropriate sensors attached and an analyzer option, I believe it's Tool Pack 3, you can have transfer functions recorded to your SQuadriga 3. You could also just do, of course, in situ run-ups if you'd like, but the transfer functions can be calculated here in the analyzer option and saved to HDF files on the SQuadriga 3 and transferred to ArtemiS SUITE later. Okay, continuing on. So now regarding sensors, Head Acoustics does not offer acceleration or force sensors, but we work with many sensor suppliers. Dytrain Instruments is one of them, and Kevin Mustor will be on a little later to help us go over what accelerometer and force sensor options are available. Moving on, we can get to our analyzing of modes with the data that we just took. So time domain analysis, we do have an option for that within ArtemiS SUITE. I believe it is ASM 40, where you can link time data records to a structure, if not already done so. And then you can load the time domain analysis project to understand how it responds to a given input. So again, from our YouTube International page, this is an example of a idle startup, I believe, and the exhaust modes that are seen during an in situ measurement recording. All right, moving on. So ODS, Operational Deflection Shape. This is also an option available within ArtemiS SUITE, ASM 41. So Operational Deflection Shape can be used if you think maybe a mode might be affecting feel, or whether it be in your hands or the seat, or however else a customer might interface with the product. You can confirm with time data played back at a specific frequency to see how the structure is excited. Again, connecting FRFs to a structure that's recorded and then loading the operating deflection shape project. An example of that here, very similar to the time domain analysis project, where you have a spectrum and you can go through. This is the horizontal are the points, and the vertical are the is frequency. It's on the x-axis, and the color scale is the amplitude of vibration. Over here we have the time data associated with that mode. You can save the mode shapes here as well. Okay, continuing on, so modal analysis, so experimental determination of structural modes. So with impact measurements or other FRF inputs, you can quickly calculate where the mode frequencies lie. Understanding modal participation coefficient, minimum damping, typical structural analysis terms that you're familiar with. So you can also save these modes and understanding the frequency as well as the shape, damping information, and MPC into a list that this can then be saved in its own project into a mode shape project. We'll have to see that here soon. It's in the modal analysis example that I'll share now. So over to here, share modal analysis, mode shape calculations. Let's now open a modal analysis project with the impact data we just took. Home, Analysis, Modal Analysis Project. We're asked to first point to a measurement point library for the structure that our impact measurement was taken on. Let's find that. Now, what the measurements are that were used for the structure that was measured. And click OK. Now, all the points were connected to all the data that was taken with the measurement, with the impact measurement workflow. So we have our shape, our structure, our points, transfer function, the shape table, and a 3D map showing points along the Y, frequency along the X, and excitation level in the color. So you can point to a specific location and it shows up in the structure. Let's change our degree of freedom to the one that was actually used. It was impacted in the, or measured in the vertical Z here, and we can see which direction or which item we can see our structure and the points associated with it, the transfer function, the shape table, or what can be the shape table, and a spectrum that shows the reference point, the transfer function location, the frequency along the X, and the level of excitation along the Y. So points 1 through 20 on the base of the rotor, flatter area of the rotor,
Those are from about 1 to 20, and then 21 to 25. That is the upper or the hub of the rotor. Okay, from here, we can open the properties for that transfer function, choose what our target quantity is, decide what we're going to be looking at from our FRF for now. Look at one channel's response at a time. And we start our pull calculations, which is our automatic indication of where modes are located. It looks like from the FRF we might have a mode further up, so I've changed adjusted the window for the calculation. Looks like we have 1, 2, 3, 4, 5, maybe 6, 7 modes in here. So the highest model size typically is 4 to 5 times higher than the number of peaks that you have in this region. So we'll do 35 for now. Right now it's based on a lot of experience as far as what number might be best there. Frequency tolerance, I'll keep it beyond a 5 Hertz frequency tolerance for specific modes. Damping tolerance, minimum stable poles per mode I will keep as the default. And I can click calculate poles. Okay, the poles that show up in red indicate that they are not quite meeting our specifications. The ones that are green do show up, and they're indicated as true modes. So we can click through, right click, and then choose our shape selection cursor, where we can choose by double clicking what mode we're going to be looking at. Now how are we going to animate the mode? That's done here. We can show it by motion only, color, or by motion and color. We can have the repeat loop duration indicated here. We can export the animation when we're ready as well. This is the level of displacement that will show in the model, in the structure. And this is the color, basically the color scale based on the displacement as well. And we can click play. So perhaps a first bending mode of the rotor here at about 1099 Hertz. If we think that this is a true mode we want to save for later investigation, we can add this shape to the table. I can continue on here with the transfer function, double click on another expected mode. Looks like it might be the first breathing mode of the rotor. A little bit more complex mode. You can also auto range right click and click on the green arrows left and right, and that will automatically adjust the displacement or the color scale. So a couple modes shown in here that we could possibly investigate with our numerical model. So if we wanted to take all the modes that show up based on this model size calculation, we can do that by this button here. Anything that meets the criterion we indicated here will be added as a pole. So 1, 3, 6, 9 poles calculated, modes calculated. But we can also save the shape table here for comparison with a numerical model shape table.
Okay, going back live now. That was the modal analysis capabilities that we had there, going to show how we can calculate modes and then save them to a shape table, because we might be interested in comparing those mode results to modified structure, a CAE model, or maybe all three. So in shape comparison, we could compare experimental versus numerical, original versus modified, prototype versus competition. Basically a way to compare modes between two sets of data. We can look at the MAC modal acceptance criteria and see modes in both cases simultaneously synchronized and compare modes side by side. So we do have a video of that as well. Make that quick. Shape comparison.
For our shape comparison project, we can click the Home button, Analysis, Shape Comparison Project, and now we have the option of opening up 2 shapes to compare and analyses to compare. So we can choose our shape table here, which is automatically linked to our structure. Click Open. This is the one we just calculated. And here we can open up a numerical model that has a shape table. And we can compare these side by side, point by point, and mode by mode. You can also choose what modes are shown in either side. We can turn off a lot of the rigid body modes and maybe some of the repeated modes as well. All right, we can turn on the same motion and color, automatically adjusted, and we can try to compare shapes here. So we'll choose the first one and click play. Let's adjust the displacement and the color scale. You can adjust what gets displaced as well. Right now just the top structure is displaced. You can turn on a global interpolation, which will adjust the whole vibration of the whole structure. There is also the comparison of the MAC here, which might be fine from a single structure comparison. But what's nice is you can, instead of looking at the two individually, you can compare A with B. So you have a single MAC show up. So a few modes lining up perfectly. Some further investigation might be needed to understand what the differences are in the modes going forward.
Okay, so that was a way to do an investigation of some mode shapes, comparing two anyway, two sets of mode shapes. What's coming now with head acoustics, and actually starting in version 13.5, we have neural networks coming for pool calculations. So as I mentioned before, there's sort of a rough idea on 4 to 5 times the number of visible modes seen in an FRF. Well, now neural networks based on neural networks will suggest a model size for curve fitting. Less user experience is needed for this. So basically, a lot of experience that was put into this neural network in order to help you automatically set your model size. And also coming is multiple reference measurements, so you could have multiple references available. References are visualized in the 3D model, and then it can also help with detection of repeated and pseudo-repeated roots. Again, coming with 13.5, you can define your own flexible chart. So instead of the 2x2 that we had there, could have a number of rows and columns chosen, as well as options for what go in those diagrams. There's also some more MAC mode and group mode options available in the charts. So again, trying to make it flexible for those expert users looking to get the most out of their modal analysis investigation. Pairwise, none, all for your animations. So quite a few animation options available as well. Presets to help you save and restore user-defined configurations. So again, a lot of options available to you, a lot of flexibility coming with 13.5. So in summary, excuse me. Recording is possible in many ways to investigate vibration shapes from structural to vehicle level and impacts inputs to in situ situations. Fully integrated into ArtemiS SUITE as of version 13.0, structural analysis family of modules. So ASMs 40, 41, 42, and 43. For those that did have ASM 18, now you have ASM 43 for the impact measurement and ASM 30, I believe, for the sound intensity. And again, coming with 13.5, multi-reference modal analysis, neural networks for pull calculations, and a lot of flexibility for the layout of diagrams and comparisons. And a lot can be said, but mainly modal analysis is done with Acoustics.